You'd get a requirement, you'd basically say, I'll do a database search or run a database query, get this data. Based on this data, I'm going to do X something else, right? Programmers were the ones that were writing code to orchestrate all this stuff. Now the agent is able to figure out those things and then orchestrate all these tool calls based on this context window, right? That's the biggest innovation that has happened between the pure LLMs and the reasoning models and where this agentic stuff comes into play. And why does programmers' jobs feel threatened at this point? The beauty of code is that it follows set of rules. The syntax is extremely fixed. Once you learn a pattern, you can apply the pattern repeatedly again and again. There's nothing, it's not a poem. It's not poetry, it's not prose. There's no new words coming. There's no creativity in there.
All right, and there we are. So today, Satish will give us or teach us some lessons on how he uses and leverages AI. I think we'll talk about OpenClaw, perhaps also Claude, especially like the top tier tools that most of us are either currently using or we hope to use in the future. I think you will do a quick demo, right, of how you use it, share your screen. So yeah, I'm excited for that. And with that, I would say, how about you just start and teach us some AI lessons?
Yeah, so not about the AI lesson, but the way I'm going to start the conversation is just give you a sense of how has this whole field evolved from people are amazed at how fast things move in this particular space. The whole mood changed within February in 2 months since the beginning of the year, where everybody now thinks software is done, software engineering is done. I have not seen an industry shift to happen in 2 months' time where the mood changed that fast. So I'm going to trace a little bit of what exactly is ML, what is AI, what are the antecedents of it, and then we get to what does the current look like. I don't have any grand theories of what the future is going to hold for any of us, but I'm just going to set the layout of the land. And then, along the way, I'll talk about what is OpenClaw, why is it so exciting, what is the state of the art at this point, what does the current future look like. This is more of, giving you a sense of what this field looks like internal coming from inside for somebody out. Very little about, hey, what is the right way to use Claude or what is the right way to use OpenClaw. This is more setting the context of for a lot of people, again, I'm talking to you about other stuff that you guys have depth in. So this is my way of saying, hey, here's something, I know something. I'm just going to present it. Okay, let me share my screen. Then we go from here. Can you see the PPT?
Yes, I can see it. Perfect.
Okay. So I'll start with a bit of a technology landscape overview. I'm not going to spend a lot of time on the history of it, but it probably is useful in terms of just setting the context. So this is what I'm thinking about, machine learning, deep learning, generative AI. What is this thing called as transformer? You'll start hearing about this stuff fairly, very regularly once you get into what exactly is Gen AI. And, the buzzword since the last year has been reasoning models. What exactly are reasoning models? And now the most coolest thing is agents, OpenClaw, how the agentic stuff works together and things like that. So that's the, all right. So classical machine learning is where, this field kind of starts, where it all began, which is how do you teach computers to learn from data? If anything, this field starts as its origins in what we call statistical machine learning. And, there are for almost a long period of time, there were certain workhorse models of classical machine learning, right? So for example, in traditional programming, you get rules and data and you get answers. These are deterministic way of saying, if this happens, do this. Or if this happens, here's my if-else conditions, give out this answer, do this math and do the answer. In the case of machine learning, it's kind of opposite, which is we give the data and the answers and we say, what is the rule that you can think of? In mathematics, this is called curve fitting. You fit a curve to existing points of data. You have a lot of other transformations like Fourier transforms that basically try and fit a mathematical function to an existing data set. Machine learning is very, very similar to that, which is you have a bunch of observations that are happening in real life. And you basically say, here are a bunch of parameters that I think determine what is happening. And how about you tell me what the coefficients of these parameters are? And then that becomes a model, right? So at the beginning, almost until 10 years ago, the primary mode of predicting what somebody would do, whether are you going to buy a car? What is the price of this particular house? Typically fit into what we think of as, today it's called classical, but back then it used to be called standard machine learning models. These came in 3 flavors: supervised, which means that you had examples. You could observe prices in a particular neighborhood over a period of time for what the house is sold for, and then basically build an algorithm that says, if it's got 4 bedrooms or if it's got bathroom, the distance from subway is this much, the price is going to be X, right? In that case, you said the bathrooms contributed more or the distance from subway contributes more. Based on that, you would basically have a linear equation that says, if the bathroom was 1 less, then the price would fall this much. This is what we call supervised learning. You have data, you train a model, you created a function that basically predicts based on the data. Unsupervised learning is the case where you do not have what you call data as such. You just are trying to figure out, what patterns can I figure out from the data, right? You have a store where people come in and buy stuff, and you're trying to figure out, some of my customers fit into a particular pattern. There might be people who search for like 15 minutes and buy nothing, and there might be people who buy something in 5 minutes. Are the different group of people? Can I separate them based on where they come from? Does iPhone lead to more sales versus Android lead to more sales, right? So this is stuff where you don't exactly know what you're trying to look for. In some sense, you're searching for like nearly in the haystack. But this is basically saying, here's a whole bunch of data that are there. Tell me the pattern that you can find. This is called unsupervised learning. You're not training anything model. You basically are asking the model to figure out lessons from there. Next came what is called reinforcement learning. This is probably like late 2000s, early 2010s is when this model started becoming popular, where the goal was, you basically build a model, like a linear regression or any kind of like standard model, but then you basically penalize the model for making mistakes, right? When we say penalize the model, ultimately these are models that run on what is called as an error function. So mathematically, this means, you set up a bunch of parameters and you try to run, and technically it's called gradient descent, but all you're trying to do is find the best parameters that give you the maximum accuracy. And the accuracy of what the model predicts versus what the accuracy of the data that you have is called as a measure of error. And then in the case of reinforcement learning, what we would do is we would penalize the model for making certain kinds of errors. You would basically say, if you make this less error, I'll give you a reward more, right? So some of this stuff comes into things like, some of the more early models that used self-driving, basically worked on reinforcement learning methods. You basically reward the model for making a good decision on when to stop or move, and you would basically penalize the model if it made a bad decision. So that way the model learns on making good decisions most of the time. Most of the game playing models like AlphaGo and whatnot typically run on reinforcement learning. This is where if you take a particular path in Go or chess, if you take the right thing, you can give it a reward. If you make the wrong decision, you penalize. So the model kind of keep learning based on that. Where we hit the limits, and classical machine learning actually is pretty old. One of the most commonly used classical machine learning that everybody should be familiar with is linear regression, right? And a cousin of linear regression, also called as logistic regression. Linear regression is still the workhorse model for almost every classical, ML method. Then there are other method models that you might have heard of, something called as nearest neighbors. You basically predict something based on in a spatial dimension, like how close is it to whatever is its nearest neighbor, because you think they're closest in a space, that is more likely to be something that is similar to that is the closest to it, right? So these are your standard MS models. Where did they hit the limits? Feature engineering, which means that you had to know what features are important that should be in the data. If you're predicting house prices, then you would put in your mental model that says, I'm going to use bedrooms, bathrooms, square foot size, distance from X, whatever, right? If you did not put a particular feature that was critical for it, maybe taxes, local taxes, or maybe availability of X, Y, and Z, earthquake proneness, whatnot, the model never actually knew what it actually did not know, which meant that ultimately it came down to a human judgment to basically say, here are the features that I think are important. And then once you put in the features, you basically go from there and say, this is what the model predicts. But you always run into this case where it is like the unknown was always unknown, so to say, right? The number 2, scale constraints. Most of the classical machine learning models are trained to run on a single machine because the underlying math, which is essentially matrix multiplication, assume that entire data is available and fits into a single CPU. Scaling it to a distributed model where you could take this model and do the math across multiple GPUs/CPUs was something which came very late. And the advent of it really was when cloud computing really starts, right? So scale constraints meant that the biggest model that you could build really was something that you could run on a CPU. So things such as random forests, SVMs, these vector machines, all these, they could use massive datasets, but then you always came down to the fact that you would take a sample of the dataset and then you train the model on top of it, and then you'd go test it on the data set that is actually held out, right? Which meant, even though you had like lots of amount of data, you really couldn't train it that much. And then these models, miserably fail when it comes to unstructured data. Unstructured data basically means like, as the internet took off and like more of the information came via text messages, your Twitter feeds, your Twitter text, or even like images, YouTube videos, comments. All of these have predictive power, but your classical ML typically relied on, things being numbers alone. So it just couldn't scale to these things. All right. So deep learning is something that started to come somewhere towards like, mid to early 2000s. Jeffrey Hinton, the Nobel winner from last year, was the primary pioneer of this stuff. And then like Lian Kun, the Facebook scientist, like these are father figures when it comes to deep learning. And so the work that they've done is seminal in terms of this stuff. Deep learning essentially is, instead of like a single model, you basically think of it as multiple layers of models. When I say layers, basically you get some raw input data. The layer one, for example, if you think of this as an image, the layer one basically figures out where does the edges of the image start and end. Layer two figures out what the shapes are. Layer three figures out, what the actual objects are and so on. When I say these things are layers, the way to think about these things is every layer is essentially, think of it as a linear function. A linear function is ax plus by plus cz is equal to some number, right? So every layer essentially is a linear function. When standard early mathematics, ax plus by plus c type thing, right? So when we say parameters of the model, what we mean by that is if you build a linear function called ax plus by plus cz is equal to 0, a, b, c are called the parameters of the model, right? The number of variables are x, y, and z. Those are essentially, they define the complexity of the model, right? So A, B, C are called the weights of the model, and X, Y, and Z are called the parameters of the model. So actually, you have a model that is a 3-parameter model, and your secret sauce literally are those weights. If you build a model that basically predicts out, property prices based on bedrooms, bathrooms, and let's say square foot size, that's a 3-parameter model, and the weights of it basically determine, how much each individual thing contributes. The way to think of a deep learning model or even a Gen AI model is an extremely large linear equation, simplistic way of putting it, but it's an extremely large linear equation where when we say, llama 3D, all that means is there are 3 billions of X, Y, and Z's in there. And when Facebook or OpenAI says, we have model weights, that's their secret sauce. So ultimately what they're solving for, or what the model solves for really is just that. It solves a linear equation behind at the back of it, the model weights being the secret sauce that they generate by training, right? So those A, B, C are those model weights that come out of the training data. And these parameters, these X, Y, and Z's are the parameters that simply just keep on expanding. And when you say it's a large language model, the large comes from the fact that you have 3 billion parameters in one of the smallest of the GPT models. The current models typically have like close to 530 billion parameters or so and so forth. I think I'm not kept track of, but I think the closest GPT-4X model is like, something like, 530 billion parameters or something. So that's the number of X1s, Y1s, that are there inside the model, and the model, those things. Daniel, I'm not looking at the questions. I'm hoping like if there are questions, just, feel free to like interrupt me.
Yeah, I think there's a question by Gervin. Just came up.
This has just kind of brought something to my mind that has kind of circulated before, but and this is purely curiosity, purely just related to machine learning, nothing related to finance. When you have a model with this many parameters, this many layers of abstraction, how do ML researchers even decide what weights to assess to the different layers of abstraction? That seems like so many different decision points. Or do they even use AI to identify what the weights of these different layers of abstraction should be?
So nobody actually assigns weights to any of these models. Weights are the outputs that come out of the training exercise. When we train on corpus of data, for example, I use the entire internet text data when ChatGPT uses or OpenAI uses to train that data. What gets spit out are the weights of those models, those A, B, C that I talk about in the linear function. Those are the things that get out of the model.
Okay, understood. Thank you.
Okay. So a deep layer, so when people use this word called deep neural networks, the deep comes from the fact that apart from the input and the output, you add more and more of these layers. What research has shown is that as you kept on adding more and more layers, the model actually got richer and richer and richer. So one of the earliest models in this space is what is called as the AlexNet model. This came out of a Stanford researcher who basically collected a large number of images and basically trained a model on top of it, right? Which meant basically when they say large model, when they say multi-architecture model, or when they say deeply layered neural network, all it means is that they just kept adding more and more of these layers into the model. What you'll end up finding is that each layer essentially learns one facet of whatever is your training need, right? What that means is, even though you probably trained it on the pictures of cats and dogs, because there are layers in the model that learn where an image starts and ends, what the edges are, what the colors are, what is an image or what is an object versus what is not an object, things like that. So every layer essentially has that particular level of information. The beauty of this thing is that what it enables is what we call as transfer learning. What that means is I could essentially take a model that, let's say, figures out the edges and take only a chunk of that model, train it on a different set of data, let's say that is radiology images, right? Now, I have a model or a part of the model that knows how to figure out the edges, right? All I'm doing right now is that part of the model, that part of the problem, I've already solved it. Now I'm giving it new set of data, for example, on radiology, and now making it learn about objects that are, on our X-ray images, I suppose, right? Objects that are something else. So essentially, this layered architecture allows you to transfer things that you learned in one context and then take it and apply in a completely different context. And magically, what that enables to do is essentially reusability of these models. Like somebody trains a model on one particular data, you can start the model at a particular layer and then retrain the whole model or fine-tune the model on a different set of data. And now suddenly this new model is very, 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 trained or very unique for that particular domain of the problems that you're solving for. So the prolificness of, why you see so many models coming out so fast is because this ability to be able to transfer parts of what you've learned in one single model and then apply to a different domain and solve it. So an LLM that can generate, GPT-3 world, where you could select things like it could generate poems, it could generate rap lyrics and whatnot, suddenly is able to generate code, right? The beauty of it is you've already learned how to do part of the problem already. All you've now plugging in is basically rules about what does code look like? What does Python code look like? What does Java code look like? And then basically say, okay, now this model, instead of generating lyrics, now generate code, right? So that's how transfer learning works. And that's how this layered architecture works in this ecosystem of and why the innovation is actually that fast in this particular domain. Okay. All right. What is behind this explosion? There's lots and lots of data. GPU compute got thrown faster. So one thing I'll talk about why GPUs are so important in this. Essentially, in this layer, I said everything is a linear equation, right? What we're trying to figure out is, in very simplified terms, the way we measure how a model predicts a number, in the case of linear regression, is we basically say, okay, the model says, your price of the house should be $100, let's say, but then the actual price ended up being $95. So the error there is $5. Or the model says 100, but the price ended up being 100, but the error there is $5. And we can figure out based on what we call root mean squared error, like how far away from the mean of the error is your prediction, right? Now, the goal there is to minimize that error. To minimize that error, you work backwards from there. You do what is essentially called partial differential equations, and then you figure out what is the maximum and minimum. This is your, high school / college math, right? When it comes to computers, you can do partial differential equations for this many number of variables. And the way computers solve for it, or the way the algorithm solve for it, is by doing matrix multiplication. So once you start representing those linear equations as matrices, you can similarly minimize the error function by what is called as inverting a matrix. Again, this is math stuff. It's like it gives you bad memories. Apologies, but essentially you invert the matrix over there. Inversion of the matrix essentially means you have to do huge number of matrix multiplication calculations. So if you have, let's say, a 3 billion parameter model, so your matrix essentially is of that big of a size, right? And then you need to do the math to be able to invert that matrix and multiply a bunch of other matrices to get to what we think of as the minimum possible error based on that linear equation. Turns out GPUs are amazing at doing this kind of math in a parallel fashion, and CPUs just suck. GPUs are also used to storing large amounts of data in their interim memory, the memory that is basically used within the registers to be able to do the math, compared to CPUs. GPUs actually come with a lot more memory to be able to hold data, not for long-term memory, but just to do the math. The amount of memory that's required is actually large, and GPUs are great at doing it. The reason where GPUs are great at doing it is because this kind of memory was always done in the case of video games. So video games were the first use cases where this kind of matrix multiplication was actually performed. And that's where NVIDIA's progeny comes from, the fact that NVIDIA produced GPUs primarily for video games, and suddenly as this field took off, a similar kind of matrix multiplication math had to be done, and now GPUs are in that kind of demand. Okay. So that's the thing about GPU compute and why GPU instructions. So as I said, AlexNet moment happens 2012. This is where all the image data came online, and suddenly people start realizing you could take this data and figure out to basically take partially built models, or rather, transfer learning becomes a thing where now you can take a model that's already built on one type of data and then reuse it for other ecosystems and so on. Okay, how does this get us to generative AI? Just in terms of difference between what generative AI versus what discriminative AI is, right? In the world where before Gen AI came in, the question that you would ask of a model is this a cat or a dog? You would give an image and say, is this a traffic light or not? Everybody would have already solved for identify the traffic lights, identify the motorcycles. So we were training the model in those cases. Those were all images that somebody put together, and then we were producing the training data for it by correctly identifying traffic lights and whatnot. We were basically giving the data to the algorithm saying, yes, this is a cat, this is a dog, this is a traffic light, and so on. Generative AI, on the other hand, starts with a prompt, right? Your prompt is, do X for me, create this, create that. Then it goes further from there to start creating designs and codes. That's the essential differentiation between discriminative AI and generative AI, right? And today, what we are living with, ChatGPTs and LLMs and whatnot are the generative AI models, where everything starts with your prompt asking for something. Okay, I don't have to talk about this. You guys already know where this is and where it's going and whatnot. But let's get into what is the meat and potatoes of what is called as the transformer, the architecture that changed everything. So transformer architecture was something that came out of, if I'm not mistaken, it actually did come out of Google. And the whole field owes a lot of the stuff primarily to Google. Even the whole concept of big data, which became a thing starting somewhere in 2006 and 2007, mostly came out of Yahoo and mostly came out of Google. Yahoo was the first company that started the big data project because they were solving, they were the primary portal back then, and they were trying to solve for it. Google, with its Google Drive and the Google file system, came up with the seminal paper on how do you store lots of amount of data on cheap clusters across. That becomes a fundamental paradigm in how Google starts working. And that is the fundamental paradigm behind AWS and Azure today, the way we see it, because cloud is actually give all this stuff, the ability to store lots and lots of data on extremely cheap hardware. The transformer paper, what is called as, the paper is called Attention is All You Need. And I'll tell you what the attention thing means. But this is a fundamental paper that came out, I think, somewhere in early 2020s or so. If I'm not mistaken, I could be wrong on that. But that's the thing that fundamentally changes everything. Okay. Step back. Let me explain, what do these things mean? So essentially, a large language model gets trained on text. The text that comes out is from Reddit, from Wikipedia, from almost every known text that's on the internet. Essentially, it becomes training data in training this large language model. Okay. Now, the question is, how do these words that appear on Wikipedia become numbers? Because I've been talking about matrix multiplication, everything as numbers, right? So how do you take a word that appears or a paragraph that appears on something like a Wikipedia and then convert that to numbers? That is where this concept of embeddings come in. An embedding is essentially a vector or a matrix representation of what every word means. These themselves are done by what are called embedding models. An embedding model basically takes a word that you give it and then represents that in what we call as a high dimensional space, essentially a linear sequence of numbers, a matrix, what you're seeing over there, that essentially represents some properties of the number across multiple dimensions. So when I use the word called bond, right? A bond could mean, in some context, I could be referring to a James Bond. A bond could, in the context of a relationship, might mean a bond of marriage or whatever. A bond in a financial context could mean, a financial instrument. So a single word has multi-dimension ways of thinking about it. Our minds process it very easily. We understand that stuff based on the syntax and the context and everything. But to represent that mathematically, you need to be able to have this representation in some kind of numbers, right? So basically, the goal there is, for every word that there is, you basically have a mathematical representation called as an embedding. These are called word embeddings. Google was one of the first pioneers in this, and then a lot of these embedding models came after, right? The goal there is once you represented these numbers as these words as numbers or vectors in a multidimensional space, you should be able to do something like this. King minus man plus woman is equal to queen, right? So now you're in a multidimensional space. King is when one line of a vector, man is another line of a vector. And you're basically saying, if I combine this vector with this and add that vector, ideally I should get another word that should represent the word queen. Right? Now you went from words into what words mean into something like a vector representation of the dimension of these words. Right? So this is the first step that happens where every word, every letter, everything that you type when you ask ChatGPT gets converted into an embedding for it, number representation of that particular word. Okay. And then what we build, what I call as these embedding space. So essentially everything that belongs to one particular domain of the space. Now that these numbers are already there, now you can represent them on some kind of X and Y axis or some kind of high dimensional space where all the words now cluster together, right? So you should expect them that like words that belong to some kind of royalty will live together in one particular embedding space. Things that represent animals live in one particular embedding space. So if you think of this as a two-dimensional vector now, suddenly these words are things on a particular spatial matrix. And now you can talk about relationships and whatnot, right? If you're generating a text about dogs or some kind of animals, chances of where you need to look for your next word is probably going to be close to be over there, right? So what this does is that it takes a word, converts that to a number, puts it up into some kind of high-dimensional space. Now the model can reason or at least think of these words as numbers rather than as words anymore. Like it doesn't know what the hell the meaning of the word any means. All it is essentially a string of numbers in some particular spatial dimensions. Okay. So basically tokens, right? So this is a word that keeps token. What exactly are tokens? In this case, the basic sentence like the cat sat on the unhappiness, it's a meaningless word sentence, but like essentially this gets converted to tokens. A token essentially means, simplest way to think of a token is essentially these are words. Like every time you do a space, this is a token. But because tokens are expensive to process and whatnot, we don't, the algorithm doesn't always need the full word as such. Like for example, unhappiness, right? Un is a special word. Happy, I really don't need the entire of the word. So I basically split it up to happy, right? I am going somewhere. I really don't need that you are going, and I don't need to know the continuousness of the test. I just need the word go to represent that token. So what we do is when we convert the representation of a sentence into tokens, we essentially strip out almost all the commonly used stuff. Like the typically has no meaning, has no value in terms of thinking about what you're talking. I can represent most often. I can take off the articles and still understand the meaning of the word. So those get thrown out. Any continuous forms of the words, any past continuous forms of the words are basically condensed down to what we call as the root word, right? Eat will represent your eating or ate or whatnot, right? So basically, once that gets stripped out, those words are called tokens, right? So now every word gets stripped out to these tokens, and these gets converted to token embeddings, the numbers that we talked about. And then the second thing that is given to it is where does a word occur in the sentence? This is called as a position embedding. What that means is, what does a word mean, every word by word, and where does it occur inside the word? So that's called the position embedding. Both of these get fed into an LLM, whereby basically what is it calling as the input vector. Okay. The key innovation inside the transformer architecture is to use the position and the word and to basically glean which words actually mean something, which means it takes a query that you ask for it. What does token needs? What does the token offers? Like, what am I looking for? Here is what I contain. The book has a label. And then basically it does a value, which is, given that you're asking for this, I'll do a weighted sum of the vectors and I'll show you how the vectors happen. So basically all it's doing is it's combining what the word means, where and at what position the word occurs. And based on that, and looking at the knowledge it has and figuring out what is likely response for your question that will maximize this weighted sum of scores. I'll show you a visual example how to do this, right? So for example, it's a self-attention. In this case, the bank was steep, so the river flowed west, right? The focus word here is bank, right? So the attention weights in this case are basically these three words. These are the keywords like bank, steep, and river, right? This basically tells the LLM that you're talking about some kind of river, some kind of like bank on side of the river, and not about like a financial bank or whatnot. Let me show you a really good example. I'll give this to you guys after. So this is a good way to visualize what a transformer architecture is. So for example, here, I'll take an example. So artificial intelligence is transforming that. So this is the word that was there. If you look at the embeddings here, these are the number representation of the embedding. So this is the token embedding as well as a position embedding. That gets into what is called as the attention layer here. So this is the query, key, and value, right? This is the attention layer, that new deep neural net that we were talking about. So this is the artificial intelligence transfer. This becomes the query and the position. Once that is done, ultimately, once it goes through, this is called as a multi-layer perceptron. So this is the deep learning thing that I was talking about, which has multiple layers, one after the other that is looking at this data. So this is called as the head layer, as is the starting layer, and then you have multiple layers that go out of this, keep on. Ultimately, what we produce towards the end of it is, what is the word that fits into this particular pattern at the end of it. So basically what it's saying is the probability of what you call a final word fits are these, right? So technically the next word could be way with a 52% 6 probability, world is going to be 42% probability. So essentially all it's really doing is, given the sequence of words and the position where they occur, and after running through my algorithm, here is a word that is very likely to fill in the sentence, and here is the probability for it. And all you really need at the end of the algorithm is some way to look at these probabilities and pick the one that maximizes the probability. Okay, and if you really want to be creative about it, you adjust this thing called as temperature, where it says, do you want to always by default take the word that maximizes the probability? So I've decreased the temperature, which means it becomes less random. It always predicts what do you think is the most likely word. If I increase the temperature, this becomes more random. Now the probabilities of other things have gone up, so which means that now I can actually get some more creative output out of the whole model at this point. So technically you could say it's transforming the lives, field, future, whatever, right? So adjusting this temperature essentially will add more randomness to what gets predicted out. And that's how you get creative words out of your LLMs. Right? This parameter called as temperature. Again, I can pose this example on Circle. It is a good way to kind of understand how all of this stuff kind of fits together. But yeah, that's pretty much what how most of this Gen AI stuff typically works around. Questions so far? I don't know if I'm okay. I'm assuming you guys are getting everything.
We have a question from Gervin. I also have some in my mind, but I still want to wait until the end because I kind of feel like that might still come up.
Okay.
Jeff just said it's impressive. Like I learned so much today, I kind of need to process it. But yeah, Gervin, you have a question.
Yeah, 2 quick ones. One, I'd love to get the deck after this and just kind of look through it again because, like you said, there's a lot to process here. The other question is, with pure curiosity. I mean, obviously these AI models are running through so many calculations to come up with responses. This is all ultimately happening. All these calculations are ultimately happening at some physical layer on the chips. I mean, how insanely detailed are these chips to be able to do this many computations? Ultimately, this could probably be reduced down to ones and zeros. And so I have to assume that's why, things like ASML and others have the moats that they have.
Yes. So to give you an example, a single model training typically runs, for example, like GPT, early GPT models typically run one training run, which is you take all of the text data that's available in the world and then you train, GPT-3 or GPT-4 model, typically is hundreds of millions of dollars. That's the cost of a training run for a model. It typically used to take about a month to train a model, or longer than that to train a model to be able to do that. You're training a 530 billion parameter model on top of all of this data, and these are for like a month or so. You're running it 24/7. I do not know the cluster. You can figure out from the cost of the model to figure out what the underlying cluster size is. These are the number of those, the earlier generation Nvidia chips that you would basically stack it up to train these models over there. The second part of the question, I think what you're hinting at is the training takes this kind of infrastructure, but when you use an LLM, you really are not using the GPUs anymore, because once a model has been trained, the model comes out with an extremely large linear equation with a bunch of weights. That model is available for you to be able to run and use. That model can comfortably run on actually CPU-based infrastructure. You don't need GPUs anymore after that. So that part of the world is called inference. So inference typically runs on, I won't say like commodity hardware, but pretty good hardware, but it's not the GPU hardware that often is used. Now, that does mean that GPUs don't have a purpose? No. GPUs still have a purpose because enterprises still want to retrain models. There is more fine-tuning that gets done. You take a ChatGPT LM and you train it to based on your data and whatnot, right? I talk about transfer learning stuff. So GPUs are still in the play. GPUs demand is still there. It's not just about the LM providers, but this is two separate worlds where there's the training part of it and there's the inference part of it. So I hope that answers the question.
That's it. Thank you.
I would have one question too, because it kind of goes into the same direction. If we apply this to the company level, which I'm kind of always doing because, I research companies most of the time, what do you think this says about, for example, the trials that companies like Amazon but also Google have with their own chips? Is it something that you see, or like how large, if you want to, kind of ask the big question, is the moat of Nvidia in terms of the complexity of the chips that you need to build? And why are the companies like Amazon trying to do the same? But then also say, for example, in the last letter, that basically, if you compare the price and what their chips can do, it works pretty well, but they cannot yet reach Nvidia. And does that matter in the long term?
Yes. So why does Nvidia have a moat in this space? Why can't other chip manufacturers replicate the same thing? So I'm going to go a little bit at the hardware level. Most of these training libraries run on what are called as PyTorch. PyTorch is like the workhorse framework that came out of Meta, Facebook back in the day, that almost every deep learning library uses. Earlier, there was a library called TensorFlow that came out of Google. Somehow PyTorch it just was extremely easy to use and whatnot, and it became the lingua franca for almost all deep learning libraries and whatnot. Underlying PyTorch depended on what is called as CUDA, CUDA, which converts your instruction set that is written in a high-level language called Python in PyTorch to underlying system instructions that GPUs can understand. Okay, this CUDA is something which actually was open source for a long period of time, but actually, and I think it still is open source, is the secret sauce that Nvidia has. Right, if you can build a GPU today, but then to translate the instructions from what is a high-level language like Python/PyTorch to underlying system instructions called CUDA, and to that it can efficiently run on a given GPU, is an extremely complicated problem, and nobody's been able to solve it. So Google or anybody can build out GPUs. It's not that big of a deal to build out GPUs, but to use a GPU to be able to train a model, this CUDA layer is missing. Unless you're able to replicate the CUDA layer, also the on top of it, the Python layer and whatnot, you really can't train any of these models. And if you think about it, the number of people who actually understand this thing at a level where, to be able to build and train a model, you can count them in like few thousands. These are PhDs from Stanford and Berkeley and like typically in Silicon Valley. They all grew up writing PyTorch code. They all grew up understanding how CUDA works. They all grew up learning this stuff, right? That intellectual property or intellectual muscle is available only there, and they all came up on this particular hardware. To build a whole ecosystem, even though it's like, maybe 10,000 PhDs, to build an ecosystem on a brand new, what you call tech stack from like hardware till software is almost next to impossible. So that's the mode that Nvidia has, that why, no matter what others do, even Trainium or, whatever other chips come up, they will have to fit into this CUDA level architecture. And that's where Nvidia has it.
Okay, got it. Thank you. We also have a question from Jeff, just coming in.
Hi, Satish. Thank you again. This is really good. Kind of a two-part question. One is there something fundamentally different in the code or the software behind inference versus training? And then you hear a lot of talks about agents that different companies are building to try to layer on top of their existing legacy softwares, for example, agents built over, say, CRM or Workday or Excel, whatever. So for the building and creation of AI agents, is that mostly just using inference, or are you going back to doing the training process again in the process of building the agents?
Okay. So I'll answer the first question first, and then I'll cover the agents toward the end of it. So I'll answer it over there. Yes, there is a big change between what training does and what inference does. Training is where we are figuring out the model weights, the ABCs in the simple model that I talk about. Inference is we just basically doing the math at the point of time. You know the model weights, you know the variables for, you know the values for X, Y, and Z. Essentially what you're doing is the math. And that's extremely cheap, extremely fast. So inference typically is super cheap, can run really fast. There's no more mental math of figuring out what the weight should be and what the weights are actually given to you. You're just plugging in the values for X, Y, and Z and basically coming up with a number. So that's why inference, like, Nvidia recently bought a company called Grok, not the chatbot, but a company called Grok. Like Grok makes chips that are optimized for inference. So a chip that is optimized for inference essentially needs to have enough memory to hold the entire model in memory. That's all. It doesn't have to be great at doing matrix multiplication. It doesn't have to do parallel stuff. All it needs to be is large enough to hold the entire model weights. If you have 530 billion parameter or a trillion parameter model, you just need to be large enough in terms of memory to have all those model weights in memory to do the math really fast for you. That's what it does.
And then and then you say that you're going to talk more about the agents later, right? So, and then another question is, and forgive me if these questions are elementary or maybe they don't make sense, but I referring to, I hear certain companies, for example, Palantir, or companies that are working with big data or historically fragmented or siloed data, and then integrating those data like Snowflake or in sort of a unified data structure. And Palantir talks about ontology, where they ties different data and build relations between the different data. That type of data unification, ontology, whatever, is that what is required for the training to sit on top of? So then the AI can then do its work on top of this unified data. In other words, can you not do training or AI if you don't have an underlying structured unified data foundation? I don't know if that question makes sense.
I'll answer it two ways. So what I've shown you is ultimately an LLM is a random word generator. But to make the LLM generate the right kind of words, to make sure that the next word is actually makes sense in the context, having an organized data set typically helps a lot. So what ontology or what having that enterprise data clear governance or clear structure helps is that it makes LLM's life easier in terms of being able to answer questions well. So I'm going to cover in the next few slides how LLMs actually answer questions and why this, why the structure of the data actually matters. So that should kind of help answer the particular piece of question. Okay, if there are no more questions, let me move further and then talk about where this takes us, right? So, okay. So I'm going to skip on the transformer stuff because we're kind of running out of time. But ultimately, what really happens is that, a transformer essentially is helping figure out a way to basically position the attention on which word is the key word in the sentence. And that gives you a way to figure out what the next word in the sequence should be. The way the LLMs work is that this stuff happens recursively, right? The moment LLM predicts a word, now the entire word so far or the sentence now becomes input to the LLM. It just keeps on repeating in the loop until it gets to the point where there is no more word to predict, and that's where the LLM gives you an answer. Oftentimes, you can also tell the LLM, hey, don't go more than these many number of loops to give me an answer. But ultimately, all that's happening is you predict a word out, and now add the word to your input, predict the next word out, add your word input, predict the next word out, and that's pretty much what is happening. It's when people say the word stochastic parrot, in some sense there is a lot to it. Okay, why do transformers dominate? This kind of work, training can run in parallel, which means that training linearly scales with GPU count, and that's where Nvidia gets its moat. Apart from the thing I talked about with CUDA, right? One of the biggest problems with classical machine learning is scaling it linearly was difficult, but this transformer architecture, because you can do this math in parallel. You can take a word, give it to a part of the GPU, and you can parallelize it. Happens in parallel. That makes training actually much faster. Predictable scaling. Performance improves as power law of computer and data, and universal architecture, right? You can exactly use the same architecture for text, images, code, audio, proteins, whatever it is, right? Ultimately, everything gets converted to numbers, and what's running in the training is a bunch of matrix multiplications on top of the numbers. It really doesn't matter whether the input is, image, the input is a video, the input is, audio, whatever it is. That's the reason the beauty of this thing is this model works for everything. And that makes this what is called as GPT, general purpose transformers, compared to more of these image models that used to be things like that, like this earlier, right? So that's why ChatGPT became a general purpose transformer architecture. What this means. Okay. All right. Where are we today, right? Scaling laws, which means that these laws, I mean, we've been hearing this for a while now, which is, the models are getting more and more accurate because you throw more parameters, which means now you started with a 4 billion parameter model, you went to 10 billion parameter, then you went to 100 billion parameter and so on and so forth, right? So more parameters still is giving out better architecture, which means that as you throw more data and as you throw more parameters and more compute, the models are actually getting better. This is what is called a scaling law. The theory has been that at some point you will hit some kind of upper limit or diminishing marginal returns where throwing more parameters more is not going to happen. When DeepSeek came last year, one of the talk internally was that, we've hit that thing. That's the reason DeepSeek was able to solve it with lesser amount of hardware, lesser amount of cost and whatnot, right? But ultimately, when ChatGPT 4.5 came out and the model that came after, the reasoning models only got larger, which means that there is still ways to go before we hit the limits of the scaling law. And right now, people are not predicting like if we're going to hit it in like next year or a year or so forth. Nobody knows exactly where this is going. So far, the scaling law still seems to be in the parameter of like throw more data, throw more parameters, it'll get better, right? Okay. Before I go any further, any questions that are pending? Okay. So the next layer of models that came out as part of this innovation is what I call as reasoning models. I think one of the first reasoning model that came out that took public's attention really was the DeepSeek. This is the DeepSeek moment of last year, where suddenly you had a model that was basically using the way humans reason, which means that instead of reasoning, so basically there's a concept of like one-shot reasoning versus a multi-step reasoning. Most LLMs or the ChatGPT that we were used to until like 2025 was one-shot reasoning. You gave it a prompt, it gave you an answer back, right? Instead, what DeepSeek did, and that was the core innovation of DeepSeek, was that it made the model reason, which means instead of giving you an answer, the model first generated an output of answer what it was going to give you. And then it used that input to basically reason whether that input actually makes sense. It verified its own work and then basically said, okay, now that I've verified, I've thought through these multiple layers of this stuff, now I'll give you an answer. So this solves two problems. One, it mimics more of how humans think. We take a problem, we split it up into multiple tasks, and then at every task, we basically say, this is the task that I require to do, and I accomplish the task, come back and see what the output of the task was, reason based on that, and say if it makes sense to give the output of that task to the next task, and so on and so forth, which meant you got a lot better models that coming out of this structure as opposed to one-shot models, which is what ChatGPT 3 primarily really was, right? So now almost after DeepSeek, every other model switched over to this deep thinking mode. Today, when we talk to a model, we have to basically use as a one-shot reasoning, or we have to tell the model not to reason, because there are questions where you just want an answer quickly, in which case you'll tell the model, like, don't overthink this, just do what is called one-shot reasoning, and then we get the answer. But by default, your O3 and the Claude today are all these deep thinking models. At every step, you'll actually see that the model thinking to itself how it's going to answer the particular question. Okay, so this is essentially a layout of how the reasoning models work. Take a problem, sub-steps, reason through each step, self-check and verify, and deliver an answer. I mean, at some level, this is magical, but all that's really happening is, you're basically training the model not to answer, not to immediately, once it generates a bunch of sequence of words as output, not to quickly give it the output back to the user. You basically say, take the output that you generated, regurgitate it on top of the same output, and then that just makes the model, basically what we call the reasoning model, right? And surprisingly, this improves the accuracy so much more that suddenly it becomes like amazingly good that, it can solve math, it can compete with, math Olympiad problems and whatnot. Just this tiny, small little change of how you want the model to be able to answer. Okay, so this reasoning innovation basically added a huge performance leap in terms of where the model ecosystem start to go. In some sense, you could argue like this is the current state of the art of where all the models are. I'm purely talking about the LLMs themselves. I'm not talking about agents and all of that stuff right now. Purely, where is the state of the art right now? The reasoning models with, for example, Claude, Sonnet, these are probably where these models are. So the way you can check this difference is, Claude has a bunch of different models that you can use. There's Sonnet, there's Haiku, and the couple of others. Haiku, on the other hand, is not a reasoning model, right? It's more of a one-shot model. Sonnet, on the other hand, is a reasoning model, which means it will take the time to basically dig through and whatnot. That's the reason. It's more expensive because it consumes more tokens. Okay, so let's get to the agents, the hardest thing that right now. Okay, so what makes an AI agent, right? Now, you take the, so when we think of an agent, you should, like, the way we think about an agent is essentially, an LLM on its own is essentially a question answer engine. There is a bunch of knowledge that the LLM has. The knowledge essentially is cut off on the day the training was complete. So all the training data that was given to, let's say, your model from 6 months ago, that is all the knowledge that is sitting inside the LLM, right? At the end of the day, an LLM is just nothing but, it has a bunch of corpus of knowledge that it learned during training, and it doesn't know anything else after that. But we work with an LLM in the current space where we wanted to actually look up newest data. Go look at the web and basically tell me what is the latest of this thing is. I wanted to look at the data that I have, which is my files, my data sets, my spreadsheets, and so on, right? And then, but we want the mechanism of how to think still be the same thing. We wanted to break the task into multiple tasks. Do goal setting, adopt and strategize, look at the available resources and whatnot, and then think, right? An agent is essentially all that, right? The brain is still the LLM. What we give the agent, though, is the ecosystem around it, which is called as what it can perceive, which is, hey, go look at the browser, use the browser and get this data. Consume an API, get this additional data from the API, or take a look at the file sitting on my folder and like do X, Y, and Z for me, right? So essentially, an agent is something, a combination of all of these, where it basically takes all the data or the stuff that's available on the browser or on your file folder or your files and whatnot. Based on that and the question that you ask for it, it reasons and plans. Okay, here's the 5 things that I'm going to do, which is the act part of it, and then just keeps and learns and keeps repeating the loop. Right. The common word in parlance for it is what is called as a harness. So we call this as an agent harness. Right. An agent harness is access to the data that's sitting on your desktops or some particular ecosystem where the data lives. In this case, in some cases, for example, Jeff, you were asking about what happens in Palantir, right? The LLM is still the actual reasoning and planning part of it, right? But the agent harness now involves data that comes from your databases. The ontology now becomes a thing that that you can provide to the agent and say, here's the ontology of how my datasets look like, right? Here's where I have my inventory data. Here's where I have my supplier information. Here's where I have my XYZ information. And Palantir simply builds an ontology on top of it. Now the agent can look at that data and then reason about it right now, right? That's why the LLM can look at the data and reason it. The whole thing is what is called as an agent at this point, or an agent harness. For example, if you guys use Claude Cowork says, hey, give me access to the files on your folder. Give me access to an MCP server or an API that you use to get data, right? What you're creating is essentially an agent harness, right? The brain still is sitting in Sonnet on Claude's servers, but by giving out this information, your files and that, you basically are building out an agent harness. And now it is able to do work for you, right? Quickly, the LLMs standalone are generally kind of useless, apart from like stochastic parts of sending stuff. But suddenly you give it all this contextual information that makes an agent so much more powerful. And that's where it brings to this concept of what is called as the context window, which is given all of this stuff, how much does an agent consume and how does it reason, right? And this is where we keep talking about, Sonnet has 1 million tokens as context, right? A cheaper LLM probably doesn't have that much context. So when you provide all this information, your file data, your X, Y, and Z, ontology, let's say for an enterprise, database data for an enterprise, or your spreadsheets or APIs via MCP servers, all these basically constitute what is called as a context window. So when a prompt goes to the LLM to do something, this entire context is being sent to the LLM. The system prompt, which basically tells the LLM how it should behave. If you're doing financial analysis, for example, then you're basically saying you're a financial analyst. So now the LLM knows that you're talking in the context of finance. So I'm going to turn off, when you say a bond, I'm not going to think about James Bond. Those nodes that are there in my model, I'm going to set them to 0. So the weight for James Bond and James Bond is 0, which means I'll never think about that anymore. Now system prompt basically sets that particular neurons in my brain to the weights for the neurons in the brains to be 0. That's what system context does. The user message tells you, this is what I'm going to be working on, right? The conversation history, the uploaded documents, all of this tell me the additional context. Then there is this case of tools. Tools are what live on your system, and tools are what the agent orchestrates. A tool is nothing but, open up a browser or use a browser tool and go search for this, right? You're doing financial research. I open up a browser window or a browser tool and go look at all the 10K and 10Q filings from Edgar, right? That's a tool call. Open up an MCP server and get this thing from Fiscal AI, something that they would have extracted. That's a tool call. Open up your Mac Finder and find all these files. That's a tool call, right? Suddenly, these tools are things that always existed on your laptop, on your ecosystem, on your enterprise, but suddenly your agent is now able to orchestrate those things based on your conversation history and the things that you're asking for. What used to be a developer task? What did programmers do? Programmers basically used all these tools to accomplish your workflow. You'd get a requirement, you'd basically say, I'll do a database search or run a database query, get this data. Based on this data, I'm going to do X something else, right? Programmers were the ones that were writing code to orchestrate all this stuff. Now the agent is able to figure out those things and then orchestrate all these tool calls based on this context window, right? That's the biggest innovation that has happened between the pure LLMs and the reasoning models and where this agentic stuff comes into play. And why does programmers' jobs feel threatened at this point? The beauty of code is that it follows set of rules. The syntax is extremely fixed. Once you learn a pattern, you can apply the pattern repeatedly again and again. It's not a poem. It's not poetry. It's not prose. There's no new words coming. There's no creativity in there. It's literally the way you write a Python code has not changed. It doesn't change because language doesn't change, which meant for LLMs, predicting the next word is actually pretty easy. There's no randomness involved, which means code automatically becomes a first-class candidate to be automated by the LLMs. And that's the beauty of this context window plus the LLM's ability to predict and the tool calls.
I want to have one question at this point. Considering the agents now, and also the fact how these models learn, and I think you will talk about OpenClaw in a minute too. So why was it that Claude at some point just felt so much better compared to Gemini or especially ChatGPT? Is it mostly because of the agent? Because I feel like Claude has been the first one where the agent actually felt like it could do stuff that, for example, the LLM in itself in ChatGPT couldn't do. Is that what made Claude so much better and also OpenClaw after that?
Exactly. So the context window, the ability to be able to use this context. For example, you look at Claude, the way it took off is programmers saying, oh my God, this is so good. It's able to do all this stuff that I used to do as a programmer before, right? And then suddenly everybody realizes that the way it orchestrates the tools, the way it manages the context window, the way it basically sets up the way the reasoning to work as well is what differentiated Claude initially from ChatGPT or Gemini. Because Gemini and ChatGPT are amazingly good LLMs. But the secret sauce in this case came from the way Claude was able to set up the context window. And that's because they used Claude to build Claude code, which meant they learned how to make it so much more better working primarily with code.
Then I have another question. And then you can continue because we also don't want to go too long. But would that mean that basically, because the LLMs always are like kind of the same, almost the same at least in what they can do, and then the next big step which Claude has achieved was mostly about the agent, does it mean that you would personally say it's rather unlikely that one of the models will be significantly better in, let's say, the near future than the other ones? Because I feel like when you, for example, listen to Microsoft CEO, he says the one big risk is that one company will have a significantly better model than all the other ones, and there's basically a monopoly developing or forming around that company. To me, it seems like that the way they learn, and again, I'm completely naive and probably it's a dumb question too, but like the way they learn seems pretty similar. The LLMs currently also seem pretty similar in what they can do. So do you feel like there's still a chance within, let's say, the next year or two, or maybe let's 3-4 years, that one will be significantly better than the others because there's something changes in how they learn and only one of them, like one of the models, will actually achieve that?
I think that is true. The open secret within the industry, Databricks openly talks about this stuff. And the reason why Databricks or Snowflake generally go model agnostic is the belief there is that we will hit those scaling laws somewhere and model as such will become a commodity. There is no secret sauce in the model itself. Because like for a normal person, you would not tell the difference. At least right now you can, but in a year or two, you won't be able to tell the difference whether the underlying model is Gemini or Claude. Like it'll like even they like unless you train your model to be differently with your prompts and whatnot. Again, that is context window question, not a model question, ChatGPT, your GPT-5 and Claude generally behave similarly in a lot of different settings. Generally, the other part that I leave that most people forget about this stuff, and this is something that I kind of, at least it's my mental model there, where these model providers will have the edge is probably not going to be in the model. It's about the amount of data that they have about you. Like, if you think about 2 years down the line, the way Google search was a window into what the zeitgeist was, your chat GPTs and your chat windows will be those things, or will be these apps. The amount of information that ChatGPT had about, like, their answer when I asked them was, oh, we want to figure out if somebody using ChatGPT to build a nuclear bomb, build X, Y, and Z and whatnot, not properly. But you knew like this data was ripe for them to sell or monetize over there. So you will think about like we understand data modes very well in this group. So eventually the moat is going to move to the data and not the model itself.
Makes sense. Again, I don't know how many slides you still have, but we have 2 questions that I would kind of like to hear. First by Ryan and then Gervin again.
Hey, Satish. So thanks for the presentation. I mean, one of the questions that I've always wondered is this, and when I've asked the engineers, they don't really actually give me a good answer, but they're not working with these huge giant LLMs, like it sounds like you are. Like, how come we can't go in reverse? And so what I mean by reverse is this, is right now you need a lot of data, and then the LLMs learn from the data, and then from the data, then you create like the neural networks, and then it comes out with the answers. The reverse would be, how come you can't embed logic without data and then feed it the data to become smarter? Like, because essentially right now we have it in a place where you need more data for the system to become smarter. How come the system can't be logical and then use the data to become smarter? Here's an analogy, right? When you're like a little kid, you don't, you essentially like, if you want to go get a cookie from the cookie jar, you don't start out with like 1 million cookies and say, oh, I'm going to end up with this one cookie, right? Yeah. So the reverse is, I'm 2 feet tall. This thing is 5 feet high. And then I got to get to the jar. There's a thing called a ladder. I'm going to grab the ladder or a chair. I'm going to go up before my parents come down. And I'm going to take the cookie, but I don't have to learn this 1 million times to figure out how to get this cookie.
Yes. So the reasoning models do what you're asking for today. That's what they do. But they start with a task. Like, you have to give it a task. And then what they do is, best from what they already know, they'll come up with a list of tasks that they'll use to be able to solve it. Now that leaves the question of you ask, if you've not seen a task like this, or if you've not seen data like this before, can this solve it? The answer so far has been no. For example, this problem like this comes up in like, can LLM solve a mathematical problem that has so far not been solved? In some phase, you've not learned from data. The data to solve a problem does not exist. Most of the answers generally have been where the LLMs actually can't do that. Right? There is no creativity in any of these LLMs in the true sense of the word. Now, what you're asking is, why can't these LLMs? Why can't I embed creativity into this? There is no creativity in any of these. Even Terence Tao, he talked about how he uses this model. What he found is that these models have been great at solving mathematical problems, obscure ones where there was little or some amount of literature, but they've not been able to solve something that is like fundamentally new so far. So I don't think the creativity is probably very a human brain thing that I don't think these models can encapsulate now, or at least into the foreseeable future.
Secretly, I'm kind of okay with that answer, because that means I'll probably still have a job so long as I can stay creative, right? I'm gonna keep thinking I'm the little 2-year-old trying to get the cookie. Thanks, Satish.
Yeah.
Sorry, jumping on that one, like I think there is a lot of debate on the same topic, right? Like Ilya Sutskever, if you hear his thought, he exactly talks about the same thing. It's like, hey, child doesn't need a entire internet to learn something. So there is that's the reason he thinks current models cannot reach AGI. Obviously, there are smarter people disagreeing with him. I think it's a very interesting question.
Satish, thank you so much. I know I've been asking a lot of questions. Going to the slide that you have up on the screen, and bringing this back to the company level on the context window, is what determines the size of the context window basically the memory chips from companies like Micron and others? Is that what determines that? because I feel like having a very large context window is going to be critical for businesses as AI gets embedded into everything.
It's not the chips themselves. Like remember, this context window is now being sent to the inference side of the world. It's not the training anymore. Right?
Oh, wow.
Yeah. So the model has already been trained. The model is deployed on let's say Nvidia's Grok machines or Azure's, whatever are the inference machines over there. Right now, model at this point is basically a linear equation or a program sitting on a computer somewhere, on a CPU somewhere. The context window essentially is the entire text that you're feeding to the model in a single shot. Remember the sentence that we gave it a few slides ago? The context window essentially is all of those sentences now being given to the model. The model then takes the context window, converts them into numbers using embeddings, and then goes and looks for answers for the things that the context window is asking for. The context is the user message is asking for. And that's where, and given the model is already occupying a huge size in memory, you are now constrained in terms of how many tokens you can actually process in a single shot, right? So right now, the best model, which is Claude Sonnet, I think takes about 1 million tokens. It means, again, think in terms of tokens, the way I explained, you spread the words into sentence into words, each word becomes a token. So once you have the model, and the model actually is pretty heavy, these models typically go into a few hundreds of gigs. An open source model goes in 6-7 gigs. So if you have a single chip that already has hundreds of gigs of memory sitting inside that chip, the amount of space available for your context window to be consumed, converted to numbers by embeddings, and then applied by looking at the data and then doing the math becomes limited. And that's where this context window limitation comes in. What you should expect is as the inference chips get better and better, like those Grok or chips or whatever, this context window will keep on expanding.
I'm just astounded by the technical capability to it. Yeah.
Yeah. And then there's also this thing, if you give it too much context, can the models actually remember everything? Right now, what has been observed is that, if you give it way too much context, the models typically take the front part of the context and the last part of the context, and they ignore everything else. Very similar to what humans do, which is, hey, the intro probably has, the abstract probably has some useful information, and the conclusion has useful information. I don't really care about the middle stuff. So that's what models do today. So basically, there's no clear-cut answers. All of this is trade-offs. So, as the models get better, as the inference chips get better, this problem will start to get solved, which means more and more of this, how much information can I give the model and ask it to reason correctly? That problem will be continue to get solved. So that's where it is.
I see. Okay. So it was very savvy for the Nvidia to buy Grok because the inference layer is going to be so critical.
Yes.
To businesses.
Yes, exactly. So that was a very, very smart acquisition by Grok.
Thank you so much.
Yeah. All right. Let me quickly, this is system prompt. This is said by the user. User prompt is what you would ask for. This rather than system prompt basically sets the context, sets the overarching context for the model. This tells the model what neurons to turn off, what neurons to turn on, and the user prompt base just activates the underlying neurons. Okay, so how do tools work? I talked about there's a tool use loop. The model decides to use a tool. It generates a structured request. This is where you hear the words like MCPs, a model context protocol. A model context protocol basically allows a tool or an agent to structure the request so that it can actually access something clearly. So, for example, tools could be web search, database, code execution, API call. Today, what you don't see in Claude, but what actually happens most of the time is this piece, the code execution. Anytime you ask it to do something, Claude actually generates a small bit of Python code internally right then and there, and then does the work for you. Because they cannot, if there's no way they could actually do, satisfy these 100 types of requests, but a code can do that, which means that they'll generate a piece of code right then and there. You might be seeing it or you might not, but they'll write a piece of code, start a Python interpreter, and actually does the work for you. You give it a bunch of PDF files and say, hey, get me all the trades that I've done in the last 1 year. They're writing a piece of Python code over there that is parsing PDF, that is extracting the thing that you want to extract, and then giving it to you back as CSV. So tools are the ones that make this magic stuff happen. And where does the SaaS apocalypse fit into it? Eventually, all of these things that we work, Salesforces, your Workdays, and all of this, ultimately they'll end up being a collection of tools sitting on somebody's desktop. Whenever you get a laptop or a computer from your company, eventually it'll come bundled with a bunch of these tools there. And these tools are sitting on on your desktop somewhere. And when you ask Claude or when you ask ChatGPT, all it's doing is orchestrating these things and doing it. And you'll never have to log into Salesforce. You never have to log into Workday, which is my reality today. So tools are the things that change everything. As I said, suddenly all your Salesforce, ERP, and all of these things now just become tools. You don't have to interact with them anymore. The idea of you having a fancy UI kind of goes away, because if the tools, if it's your agent that's doing the work, who the hell cares whether you have a good UI or not UI, right? As long as the stuff gets done. So there's more of this stuff. So agents are the ones that are reshaping the enterprise, where things are going at this point. And this is where things is right now. Okay, so where is the challenge today in terms of where this is going to land? You'll have multiple agent platforms. A single enterprise will have Workday, will have Salesforce, will have ServiceNow, and a bunch of these tools. And then you have these enterprise tools, right? So you have an agent that does X, Y, and Z, another agent that does a slight version of another one. So you will get into this case where what is the right way to do something? What is the authoritative agent to do stuff? So this is typically what you would have done in something like a Workday, where you would do performance reviews and feedback. I don't do that anymore, right? This was manual stuff that I used to do earlier, but I have a performance review agent sitting on my desktop. And I basically say, hey, go do this for me. And I get all the interactions with that person given to me straight up. Do I care whether Workday has a really good interactive way of, giving performance feedback? No, I don't. Right? So that's the dilemma of where do these SaaS companies fit in? Will everything just become a database sitting in underlying an API somewhere? Will any of these things have personas? Will they be distinguishable? Nobody knows. Okay. All right, OpenClaw. So OpenClaw, the beauty of why OpenClaw actually took off, and this is like funny though, is, we've been talking about these agents. I've said agent is nothing but a bunch of skills and probably an access to tools and nothing else beyond that. Right? That's what the agent is. We talked about this agent here, right? So this is what an agent is. What OpenClaw made, and again, when I say skills, skills are essentially markdown files. These are text files that basically sit, that tell the agent what to do. Tools are here's how you would call my SQL server. Here's the connection string to call a SQL server. That's a tool, really. Everything is written in plain English. There's nothing special about any of these things. Everything is basically in a structured text. As if you were writing an HTML page, you would write in what are called markdown files, right? What OpenClaw did, though, is basically democratize the idea of building an agent. He said, somebody gave you built-in skills on how to connect to Gmail. Somebody gave you a built-in skill how to connect to Salesforce. Somebody gave you a built-in skill how to connect to whatever it is that there is to connect to. Because it has tools like a built-in browser tool that uses DuckDuckGo, I think. It had a built-in tool that could scrape any website that you asked it to do. Somebody wrote a basic simple Python program and said, here's how you use a library to scrape stuff. Now suddenly you could basically spinning up an agent did not require any kind of technical abilities. You could talk to OpenClaw and ask it to spin up an agent. So if I go to my OpenClaw installation, this is my OpenClaw. And I have my Discord server that I set up. And I set up an agent over here whose name is Bertie. I'm a big PG Widows fan. So his name is Bertie. And then I can talk to Bertie and then basically say, hey, agent, go do something. This agent has skills. Here are the list of skills that this agent has. Downloading a skill is pretty trivial, where you could basically just get, if you open up any of these skills are publicly available. You can go to anywhere and, if I open up a skill, so these are all the skills. A skill at the end of the day is nothing but, a skill basically is a markdown file. A markdown file looks something like, if you guys are familiar with markdown skills, I'll show you an example of skills. So if I have my, so this is a skill. This is a definition of a skill where I'm saying, here is how you would modify, apply a skill to do something. I'm basically saying, here's my, I'm writing a migration library from one particular library to another library. And I'm saying, here's an API. I want to migrate to this thing called as alpha data. And here is a piece of code that tells you how to do this migration. Wherever you find this, replace that with this, right? This is text file where I'm basically telling Claude, and this is how you do a migration. And this is written in a text file. This is not code. This is basic text file, which anybody should be able to write. And every skill that you find in Claude are actually a combination of these skills. Okay, so this is a UI developer skill. Right? You're an expert front-end developer specializing in server and web applications. Here's the context. Here's how you do skill, your responsibilities and whatnot. We call this a skill because it basically is telling you how to write this. You could write a DCF building skill that says, and there are DCF skills that are there, which say, what here's how you go build a DCF. You can look at here's a prompt library that I was doing it yesterday. I said, here is how you would build a DCF. Here are my model premises. I'm building a DCF for this company. Now, if I go and ask my Claude, it's going to basically build a DCF model by basically using the skill. Right? So I've built a skill over there. So ultimately, to build an agent, you just need to write this text file once, and now the agent can do this thing automatically. And the way you invoke the agent is basically say, hey, use the skill and do this for me. And that's what made OpenClaw trivial, is that you could build a bunch of these skills into agents, and building an agent just becomes trivial. You can spin up a new agent simply by saying, here's a skill, and I want you to have it, go run it. That's it, right? And the beauty of it is because it comes with these channels, which meant that you could have I have a Discord as a channel, which means I can talk to Claude or my agent. I could basically say, can you research? So this basically goes to Claude, and Bertie now uses a particular skill, and then it does stuff. Like I gave it some research list earlier. It basically did that particular research input. You put it over there. So now, and then it basically saying, given the skills that I have, here's what I can do. The beauty of it is, if you're a non-technical person, this was your first interface to building out agents on the fly, asking it to magical things that seemed magical, that were only limited to developers. Like if you came from Claude or Claude CUDA one day, you knew what an agent was, you knew what the agent was doing. But then Claude basically democratizes said, just go do whatever you want to do. And building a skill became super easy and trivial. That, of course, led to security issues, because now you can have malicious skills and whatnot. But that's the name of the game. People are willing to take those risks and so on. But that's where the Claude thing just becomes trivial. Is you can have an agent that you spun up of your own. You can train with the skills that you want, and you host it on a server somewhere. And now you can talk to it via Telegram, via Discord, via WhatsApp, and then it does things for you. And in my Discord channel, I set up something for my daughter, for my this is the channel where my daughter talks to Bertie. Now I can observe what she's talking, that sort of stuff. I have a skill where I learned Spanish. So I basically talk to it in Spanish on this particular channel. So now I have an agent that is doing stuff for me specifically for that particular context of the word. So that's how we use OpenClaw. I mean, are there extremely good use cases for this that people are using to make money? Probably. But in some sense, it's a fun little exercise to spin up agents for in a simple ecosystem to kind of play around with. Okay. All right. I don't think I have anything more than that. How cloud works, I talked about this stuff. Yeah. Right now, where is all this heading? Right now, people are talking about this orchestrator agents, and you're finding this with Claude itself. Claude itself is releasing these orchestrator agents where you can have multiple things run at the same time, talk to each other, have this orchestrator agent basically listen to each other's stuff. And basically, you create whatever. In Claude Code, there's something called as agent teams. You can create an agent team. You can say, let's say I have 2 coders, I have 1 reviewer, 1 architect, and you guys all work together whenever I give you a problem. And then that's a very common thing at this point, where basically you have multiple things that are writing code and checking in, whereas the reviewer is reviewing, and ultimately the architect is the guy who decides whether something is right or wrong. So this is happening at this point. The AI stack is emerging. There's, of course, the compute infrastructure, the foundation models that are going there, and the vertical applications are now starting to happen, which means you will see what we're seeing with, Anthropic going into cybersecurity, Anthropic going into something else. My guess that you will see more of that stuff happening more and more. Some of the low-hanging fruit will just simply taken away. One thing I can think of is tax prep. Literally, all the information on how to do taxes is available. It's just a matter of detail at this point. I know there are people who disagree with it, saying, nobody wants to take a risk and whatnot, but that's a matter of crossing the boundary. Once you cross it, it's gone. There's nothing fundamentally gating from LLMs to be able to do tax prep and things like that. So, yeah. So that's pretty much what I had in terms of to talk about agents and stuff like that.
Well, I got to say, this has been one of the most impressive presentations that we had. I'm blown away by all the knowledge that you have on this. We still have a question by Martin, I think, who's also an expert, so this should be interesting. And then
they
we'll
raised
also
their hand before me, I think. I heard a bunch of raised hand sounds, so I don't want to jump the line.
No, you're the first. At least you're showing us the first for me.
Okay. Satish, I would echo everything Daniel says. This is awesome, and I kind of just want to have this slide deck as like a primer to reopen anytime I want to just check refresh, which is why I asked for book recommendations too in the side. This is sort of a philosophical question, but one thing, this was like a tweet from Elon like a month ago, and it made me think about things too. And you seem to be plugged into R&D, so I just wanted to know if you had any thoughts about this, or if it was like way in the future. Your comment about how Claude Code sort of works on the Python front end and spins up its own code has been something that's like, it's been poked on by Elon, where he thinks code is like a very human invention, that's it's using something that's very human, and really LLMs in the limit should be able to just work off of machine code. Like why should it need to use this human construct to interact with software when it should be able to just think at the machine code level? And I didn't know if there's like pioneering or emerging research that's going on at that level, because intuitively it makes sense, like it's using a human construct to interact with computers, but I didn't know if there's any actual traction to that idea at the research levels, or if anybody's working on that.
I do not know if anybody's working on that, but give it like a year or two, I won't be surprised. Python intermediary thing being like Python intermediary is good for us to look and validate. It's easy to understand, but definitely there is no reason for it to write Python code. Like, if generating bytecode is the way to go, that's what will happen.
Thanks.
Lawrence, your turn.
Yeah, sorry, mine's probably going to be a lot simpler relative to Martin's question. But firstly, thank you so much for the presentation. I just wanted to ask, obviously then the context window is incredibly important, but obviously with the limitation with the length and the memory available, are there kind of methods to improve it? Like, does the RAG kind of improve the context window, or is it something? And yeah, I guess that's my main focus.
So RAG doesn't quite really improve the context window as such. What RAG does is improves the quality of things that you put in the context window. So for example, RAG is, when you have like a vector index of databases or documents that are sitting over there and you ask a question, you want your LLM to look at the data from the documents and answer the question. What RAG allows you to do using some techniques is to say, out of the 50 documents that I want to look at, there are only 2 documents that are most relevant. And I want them to be either up in the context window or be only included in the context window. And I want the other 50 to be excluded, 48 to be excluded, right? RAG is primarily a technique at that. And the hierarchical searches that you run to get the right element information basically help you set up the context window more accurately, because your LLM accuracy or the quality of the response is going to depend on what is in the context window. So the RAG basically helps with that stuff.
Oh, perfect. Yeah. Thank you. I appreciate it.
All right. I would say if there's not a single last question that we can take, then we would close it. So is any question left open? We get one last from Pope, please.
Yeah, hi Satish. Thank you so much for these slides. I have kind of maybe simple question. If we assume like all the data, all the information is open to anyone, any agent, and does it mean for LM, it just needs to invest as much as it can to build the computing power, then it can reach the top, and we cannot really have we cannot really tell what's the difference between these LMs. Does it mean like that?
I mean, that will be the goal eventually. Like, nobody should need to know what is the underlying LLM. As long as it is able to answer the questions based on all the stuff that there is, you really don't need to have to, like, I mean, that's what Daniel's question was. Will LLMs become a commodity? At least the inside thought is LLMs will actually eventually become commodity. Yes.
Okay, just because if I look at those companies who are investing huge in LMs, or to say the AI, like the Meta, like Amazon, whoever just tell the investors they're going to invest big, then their share price drop. That's why I consider that it's like people can't see an end to this war, and there's
So-
no other big difference.
So there are two schools of thought, right? Like, what has happened is context windows have gone up. The price of inference actually has been falling significantly in terms of what it has been earlier. Now, there are two ways to argue. Companies like OpenAI and Anthropic are selling things that is losing in terms of purchasing power value, right? Hey, you're selling a product that is losing pricing power or is becoming cheaper by the day. Why would you want to keep selling it? The flip side to that is the Jevons paradox that people talk about, which is more and more people will use it. So the commodity, the value of the overall ecosystem will go up and whatnot. Both of things could be true, where software becomes so cheap, which means that you should technically have more software. That is what you should expect to happen. But I think the beauty of this is when will that inversion happen? My thing is it's probably going to be a year or two. I'll give you an example. I started my career not engineering, software engineering, but primarily in data science and data world 10 years ago. And the pace at which things have moved and the stuff that I used to do 10 years ago versus what I do today is just mind boggling. I've never seen this much amount of pace where my skills so rapidly degraded. It is the first time, I feel like an idiot. But that said, I've become more valuable to my customers simply because I have so much wealth of knowledge, what they value, rather than because whatever I was doing 10 years ago, building these machine learning models or whatever. Nobody cares about ML models anymore. That's what I used to do 10 years ago. And now, even though my skills have degraded, that's not what I'm getting paid for. So I think that is what you'll be finding in your LLM world as well, is a lot of the stuff will just simply be go away, and more of this will be getting used, more of this, that's what I think eventually it'll end up being. So.
All right, perfect. Then once again, Satish, thanks a lot for the presentation. It has been absolutely fantastic, and we will get your slide deck. We'll post it below the video call. I think that will help a lot of people. And maybe also Martin asked for some book recommendations. If you have any, you can also just text me them, and I will also put them into the description. So awesome. Thanks a lot, and see you all on the next call.
Thank you, guys. Bye.
Have a good one. Bye-bye.
Thanks for listening to TIP. Follow the Intrinsic Value Podcast on your favorite podcast app and visit theinvestorspodcast.com for show notes and educational resources. This podcast is for informational and entertainment purposes only and does not provide financial, investment, tax, or legal advice. The content is impersonal and does not consider your objectives, financial situation, or needs. Investing involves risk, including possible loss of principal, and past performance is not a guarantee of future results. Listeners should do their own research and consult a qualified professional before making any financial decisions. Nothing on this show is a recommendation or solicitation to buy or sell any security or other financial product. Hosts, guests, and the Investors Podcast Network may hold positions in securities discussed and may change those positions at any time without notice. References to any third-party products, services, or advertisers do not constitute endorsements, and the Investors Podcast Network is not responsible for any claims made by them. Copyright by the Investors Podcast Network. All rights reserved.
And Peter Thiel likes to talk about how disruption only tends to happen when you have a product that is 10 times better than a previous sort of incumbent product. And that's because of these switching costs. Human habit is very regular. It's very hard to change the way people do things, and they're not going to change for no reason. 20%, 50% cheaper. In this case, it's probably not going to do it. The least of which, because they're also going to be skeptical it's actually cheaper. Because if there is any errors in this AI code, they're going to have no idea how to fix it, and it could actually end up costing them much more money.